Let's see. Let's look at what Kirchoff's laws are. As usual, using this. It can be called Kirchoff's rules. There are two rules. The first one says, it talks about an electrical junction. An electrical junction is where many conductors meet together. And it says that at any junction, the sum of the currents that flow in is equal to the sum of the currents that flow out. Again, the total current that's coming into an electrical junction is equal to the total leaving the junction. That's all. And you'll understand this as I go along and try to show you a circuit and how it's applied. Now this rule is also called the junction rule because it's applied to a particular junction. And I'm sure you know what a junction is, where many conductors meet together. So that is the junction rule. The second rule is called the loop rule, and it's applied to any branch of the network. It's called the loop rule. And according to this, if you take the changes in potential around any loop and add them up, you should get zero. So the sum of the changes in potential, and you know that potential means voltage, right? So you take the sum of the changes in voltage around any closed loop of a circuit, you must get a zero. You must add up to a zero. And it's called the loop rule. Let's see how this is applied to an electrical circuit. First, I have a very simple circuit which you could have tackled using Ohm's law. And by the by, Kirchoff's laws are an extension of Ohm's law. Ohm's law can only be applied to simple circuits, but Kirchoff's laws can be applied to complicated circuits. Does that make sense that you're seeing there? In the first circuit, on the top you have the battery of EMF E, the current flowing is I, and you know the current flows from positive to negative. It flows through a resistance R. Now the way you apply Kirchoff's laws is very important. If the current flows, now you start the loop in the clockwise direction. On the top loop, you can take the counterclockwise or clockwise. But let's assume that you're going around the clockwise direction. So will you be going in the direction of the current? Yes. Clockwise is in the direction of the current. So that current is flowing through the resistance in the direction that you're taking the loop. Therefore, the potential drop will be negative. Again, if you go around the loop in the direction of the current through a resistance, then you're going to get a negative potential drop. That's why you see negative IR, because according to Ohm's law, the voltage is I times the resistance. And then when you come back into the cell, what's the direction in which you're going to move? Aren't you going to move it from the negative to the positive? No. Aren't you going to be moving from negative to positive like that? You're going from the negative to the positive, therefore the voltage drop is positive. Now I told you two things. If you're going from the negative to the positive of the cell through the inside, you'll put it as a positive. If you're going through the resistance in the direction of the loop, then you will take it as negative. That's why I got E minus IR is equal to 0, which means E is equal to IR, which is simply Ohm's law, isn't it? Okay. Since we are going in the same direction as the current, the potential drop across R1 will be negative. So you can go ahead and write negative I1 R1. What about when you come across R2? Again the same, isn't it? The current is flowing in the same direction as we're going across the loop, so it's going to be negative I2 R2. and keep going around same way. And then when you come here, it'll be I1 times R2, because the same current flows through R1 and R2. When you come across the battery, you're going from negative to positive, so it must be positive, right? Therefore, when you apply it in the first loop, there I have labeled the first loop, and I said in loop 1, E minus I1 R1 minus I2 R2 is equal to 0. That makes sense? Okay. Go ahead. Is this what you got for loop 2? Negative I2 R3 plus I1 R2 plus I1 R1 is equal to 0. Is that what you got? Okay. Now this bridge, actually we're using a bridge method. It's called Wheatston's bridge. And you have 4 resistances connected across the 4 arms of a quadrilateral, as you can see on the board. So you have 4 resistances, and what you have in the center is a galvanometer, which is a very sensitive instrument. So the resistances are R1, R2, R3, and R4. The directions of current is as shown in the figure. Let's get all that. Okay, there you go. So you see the resistances R1, R2, R3, and R4, don't you? 4 of them. The currents, I've labeled them. I1 is the current through R1, I2 is the current through R2, I3 through R3, and I4 through R4, just to remember. And the current through the galvanometer is Ig. And there is a battery of EMF E. I'm applying Kirchoff's second or loop rule to B. Now I slowed it down now. If you look at, I applied the first law there. What's the first rule? The first rule, Kirchoff's first rule. The sum of the currents entering a junction is equal to sum of the currents leaving the junction. All right, everybody look at the junction B. That junction B has 3 currents. Please stop drawing. I1 is coming into the junction. What about I2? Leaving the junction. And what about Ig? Leaving the junction. A current entering is taken as positive, and a current leaving is taken as negative. So therefore, at B, now you should understand that I1, since it's flowing in, is positive, minus I2 minus Ig is equal to 0. Do the same at junction D. Do the same at junction D. I3 is coming in. What about Ig? Coming in, and I4 out. Therefore, I3 plus Ig minus I4 is equal to 0. All right, this is... So, then I can cross out the Igs, and I would get I1 is equal to Ig and I3 is equal to I4. Wouldn't I? I1 is equal to Ig and I3 is equal to I4? Yes. Is anybody with me?
It's almost like as if it just skipped over G.
If Ig is 0, then I1 minus I2 is 0, which is I1 is equal to I2, and I3 is equal to I4. Now, then we applied second loop rule to those 2 loops. Check whether you got this. Is this what you got? Negative I1 R1 minus IgG plus I3 R3 is equal to 0. And in BCDB, did you get negative I2 R2? Negative, I made a mistake. Didn't I? It's supposed to be what? Positive I4 R4. Okay, I'll change it. Positive I4 R4 plus IgG is equal to 0. Is that okay? Now you go ahead and again, remember IG is 0, so what happens to the product? Wherever you have IG, you put a 0. So IG becomes 0 there and also in this. So this term also crosses out. What do you have now? What do you have? Don't you have I1R1 is equal to I3R3? Yes? Okay, write it down. I1R1 is equal to I3R3 and what?
I4R4 is equal to I2.
Okay, so you have I1R1 is equal to I3R3 and what's the next one? I2R2 is equal to I4R4.